So let's see the lecture 2. In this lecture we'll be seeing a vector norm, or that is also called you can understand easily as length. It is just called norm as well, and we'll see dot product and also why all of these is necessary in MLAI. So let's start. We'll see how to compute the length, and we'll also visualize the dot product. So let's say we have a vector v like this. Sorry about that. Okay, so we have a vector like this. Now if we have to compute the length of this vector, what we'll do is simply put each of the coordinate value under root and square it. No, square it and then under root, obviously. So this will give you the length, which is 9 plus 4 13 under root 13, which is approximately 3.61. Now if we descale the vector, here we can see this value. So here we can see this value 2.86. If we are descaling, the value will reduce. Obviously the length of the vector is reducing. Now let's see the dot product. So we have two vectors, v1 and v2, and how can we get the value of the angle? Okay, let's see. This is the angle, let's say theta. So how do we calculate exactly? So for that, what we do is we are projecting this perpendicular, right? And the product of this length, this projection, and this vector on which it is being projected, the product of these will be the vector dot product. So for that we have a formula: v1 dot v2 equals to v1. This is basically the length, or you can say magnitude part of the vector v1. That's why we are representing in mod. And obviously the length will be positive always, non-negative, not positive, non-negative. And we have v2, then cos theta. So this theta is same as this angle. Now let's see how, if we change the theta, or we can say if we move the vector around the other vector, how will the angle is changing. How the angle is changing we can see here, as well as how the dot product is changing. So notice here, now on 0 this is perpendicular 90 degree. So this is a unique property that is also called as orthogonality, that we'll study later, probably in more detail. And now one thing you'll notice that it was positive before this angle, as in before 90 degree, and now if you'll guess, this will go negative. Now the dot product is negative. This is signifying that the angle is now being reversed. The direction of the two vectors is moving towards the opposite side. And so geometrically you can understand that the dot product is actually giving you the value how similar the directions are for the two vectors, uh, as in which direction the two vectors are pointing, how near are those directions. So like when they were perpendicular, the dot product was 0, and when it is completely opposite, the dot product will be the same as uh, it was here at the start. When wait yeah so at the point when these vectors will be meeting, so at the point where these vectors will be meeting, the dot product will be something around 5, I think. We'll need to calculate that, but yeah. And when the vector will come exactly in the reverse direction, the dot product will be same but negative. So I hope you are getting the idea that it is basically giving you how similar the vector is. We are getting it directionality wise, but in machine learning or MLAI, same thing. It would be like uh, in our machine learning, the vectors represent data. So how similar the data is, that's what exactly a dot product is representing. And here we are visualizing that on the graph. I hope you got it. If you have any doubt, you can comment, obviously. Now we can understand this in an abstract way. Like if you have a vector which is representing king, and you subtract man from it, and you add woman, so these are all vectors. Well, we are not really calculating the uh, text based vector representation. We are instead just taking it in an abstract way. So assuming this is the vector representing king, now if we have a vector which is, let's say, man, which is pointing in this direction, and we are visualizing this in 2D, but think of it that these will be in 3 dimensions, or maybe it could be in multiple dimension as well. So if it is just text, then it would probably be in 2D only, but if it has more dimensions, then it would be in 3D or some higher dimension which we cannot even visualize. So for simplification, for simplified understanding, we are taking them in 2D right now. Now let's subtract the man. So here I was not really able to put that into animation. So assuming this is directly being taken like this, I hope it's representing the same thing approximately. Alright, and now if we subtract this, so it will go in negative direction somewhat here, and we can add these, and when we'll add basically this vector and this king, we'll get the king minus man vector. So let's see. So this is the king minus man vector. Okay, now if we add a woman vector to this, These are all approximate abstractions. This is nothing on real data based. Okay, so don't think like that. Now assuming this is the woman vector, and let's say this was the woman vector. No, wait. Okay, so we can exactly see this is 3 unit, 1 1 on x and 3 on y. So let's represent this as woman here. So this is the women vector. Now if we add women to king, so how we'll add? We'll just put this here like this, and now we'll find the resultant vector like this. So the resultant will be somewhat like this. So let's see. And this should represent the queen, isn't it? So that's the idea. So I hope you got like why is it required, and why are we studying this part of linear algebra for our machine learning goals. So if you have any idea about clustering or k nearest neighbors, you'll get that there it would be useful for calculating the distance, Euclidean distance and Manhattan distance, Euclidean basically, uh, for visualizing the clusters or creating the clusters basically. Then okay, let me come here, and then for the similarity measures, for example, you have a recommendation engine, let's say for Netflix, and you have a data of let's say series. For example, you like Batman, so that would represent a vector, and the dot product of that particular vector uh, with another vector, let's say I don't know any movies from DC, let's say the Joker, let's say. Yeah, so the dot product of those vectors will be positive, and if you dot product that to, let's say, some anime, so the dot product will be less in case of Batman and anime, and in case of Batman and Joker it would be more, representing that they are more similar, and Batman and anime is not that similar. So that's how it is being used. And in neural network as well, we'll be using dot products with along with the addition of bias, so that is also there. Then regularization, like basically this part is for optimization, we'll see that later. So we got that these are the core thing in machine learning as well. Now I hope you are able to visualize. If not, let's try here. So I'm taking both to unit vectors right now. Okay, now let me just take some vectors. Let's say 1 2 and 3 4, I guess. So what would be the dot product? If we calculate the length, this would be 1 plus 4, which is under root 5, and this would be 9 plus 16, which is 25, under root will be 5, right? Now this and this, when we multiply these and divide by the dot product. So dot product will be like this: 1.3, this being multiplied by this and this being multiplied by this. What we will get is, so 1.3 and 2.4. This is not a vector. I shouldn't represent it like that. This is not vector, this is scalar value. So this will be 3 plus 8, which is 11. Okay, now we got this 11. If we multiply 5 with the root 5 and divide by 11, we should get the dot product. So now let's try doing this visually. What vectors we had? 1 and 2. So 1 and 2, it should be here, and the other one was 3. So 3 and 1, 2, 3, 4. So the dot product we are getting is 11. That also we got, right? Now if we calculate okay, so this angle we are getting here is 10.3 degrees, which is giving you the idea, like if this angle is closure, obviously, then it means that they are similar. Now, okay, wait, it got zoomed out. So this is like this. Now now to calculate the angle, what we'll do is simply what we did here, the dot product and dividing by the multiplication of that. So 5 root 5. So this would be 11 by 5 root 5, and it should be taken as inverse, cos inverse. That would give you 10.3, hopefully 10.3 degrees. So let's see, 5 times root 5. So it's 11.180 and 11 by 11.180, and we'll do arc cos of this in degrees. Cos inverse of okay, it's not giving me the value, so let's find out through Google only. Cos inverse calculator. So this is 10.3, something which we calculated, 10.3 right here. Okay, so I hope you got the idea. Okay, now let's move on to our Jupyter. I've already added this code here. Now let's understand what we are doing exactly. So first we are defining two 2D vectors. We have already seen this. If you don't know how we are doing this, you can watch lecture 1. Then we are printing these two vectors. Obviously we are getting 3 4 4 3 as we defined, and now we are doing the dot product here. So let's calculate this manually and verify. 3 4 3 4 and 4 3. Okay, let's do this here only. 4 3. So this would be 12 plus 12, which is 24, which is obvious, right? Okay, now if we calculate the length of the vectors, what we'll get? This is 3 square 9, 16, 25. So this length will be 5, this length will be 5, and yeah, so we are getting here 5 and 5. Now to see for the formulas, not the formulas, I mean what method we are going to use, and the syntax of Python to calculate these. You can either create a cheat sheet kind of thing, or you can directly Google or chat GPT. There's no need to remember these, right? Then we have the angle between u and v, so that we are calculating by putting the dot product first, that is 24, and then the length, multiplying the length of the two vectors, which is 5.5. So this is 24 by 25, and if we take the sine inverse of this, or you can say arc cos of this value, then that would give you the theta. So here we are taking the value in degrees, which is 16.26. Now to show the negative dot product scenario, I'm considering these two arrays, doing the dot product, and as we expect, we are getting -2 here, which is not new, right? Now we have created this if else kind of menu, not menu, but yeah, this conditional statement flow thing here. If the dot product comes out to be greater than 0, we'll get that x and y form an acute angle and they are similar. If they form an obtuse angle, then they are not similar, and you can say they are going in opposite direction. And if they are perpendicular, I would say they are unrelated, as in not even opposite, not even similar. So like that. Although this part is not really relating to the similarity, I would say. Okay, now to compute the norm difference, which would give how far the two vectors are. Obviously, if you have a vector, let's say if you have 2 points, here we have x and here you have y. So how do we calculate the distance between these? That is simply x minus y, or you can do y minus x as well, but because they are length, you will be doing the modulus, so you will get the positive distance, obviously. And so we are getting here as well this 3.16. This distance is for these vectors, by the way. And yeah, that's the Python practical part for this vector operations, norm and dot product. We already did the operations part actually. Only norm and dot product was for this video. Next video will come soon. It won't take this long. that I would promise. And yeah,